Okay. Hello, everyone. I hope you are ready for a very interesting talk. Unfortunately, I have to give the talk today. Professor Mutlu is not here today, neither tomorrow. And these 2 days, we are going to cover a very important topic of the course, or two important topics of the course. Today, we will talk about SIMD processors, tomorrow about GPUs, which are, let's say, like a special form of SIMD processors. Why are they important, these two lectures? Well, the reason is that, first of all, we are going to complete this last part of other execution paradigms. Recall that everything started with the single cycle and the multi-cycle machine, and after that, we started studying how to improve the performance, how to achieve higher throughput in the computing systems and different ways of doing this, where pipelining, out-of-order execution. In the last lecture, Professor Mutlu talked about very long instruction word architectures, about systolic arrays. These are, let's say, in this category of other execution paradigms. And now we are going to cover some of the most important execution paradigms these days that are SIMD and GPU. That's one reason why these two lectures are important. The other reason is that very likely you will have one or two questions related to these two lectures in the final exam. You can actually check last year exam, spring 2018, which is already in the website. Okay, so this is more or less what I already said. And these are the readings for this week. The required one is the first one, NVIDIA Tesla. This is an introduction to the architecture of NVIDIA GPUs. It's quite accessible paper, I would say, quite easy to understand, and especially if you read it after today's and tomorrow's lecture. And the other one, it's also a very interesting one. But it's recommended. It's about the MMX extensions, these multimedia extensions that we have in Intel processors since the end of the last century or the beginning of the 2000s. And actually, we are going to talk about them probably at the end of today's lecture. Before we go and start with the lecture, just let me make an announcement. You might have already seen this in Moodle, because some of you, I don't know for what reason, are missing the deadlines of the lab reports. We have created one assignment for you to upload all lab reports, those lab reports where you have missed the deadline. Unfortunately, there will be a penalization of 1 point. This is fair because, I mean, for those people who submitted on time, they deserve a little bit higher grade. So the maximum grade in each lab report will be 2 points. So I hope that all these rules here are super clear. You cannot submit something that has already been submitted and probably graded, of course. And you should be able to submit as many files as possible and resubmit as many times as needed before the deadline, which is obviously a hard deadline. After that, I hope not to receive any email, oh, I forgot. No, that's not going to happen because you have until June 14th, okay? So anyway, if you, I don't know, run into any trouble when you submit multiple files or whatever, just let us know and we will solve it. Okay, let's start with the lecture. SIMD processors and GPU, it's what we are going to cover today and tomorrow, and we start with SIMD processing. What is SIMD processing good for? It's good for exploiting data parallelism, and in particular, regular data parallelism. We are going to talk about this during the whole lecture. But just to give you like a very, very quick and easy to understand example, usually when you are writing programming, writing your C code or whatever, you will see that many times you write a for loop, and in this for loop you are going over an array and doing many times the same thing, right? So for example, the most easy example to understand is you have two vectors and you want to add them element-wise. You want to add A0 with to B0 and store the result in C0, A1 plus B1 and store the result in C1, and so on. So there is a lot of parallelism there. Let's assume that our arrays or vectors have 1 million elements. So we could potentially be operating on these million elements at the same time. And why is that? Because the computation that we need to apply to each of these elements, A0, B0, C0, A1, B1, C1, and so on, is completely independent, right? So why don't we design a machine that can operate on all these elements at the same time? Unfortunately, it won't be possible to design a machine with 1 million functional units, but maybe we can create a machine with 128 functional units, and then what we will do is iterating 128 after 128, right? That's essentially the idea that SIMD processors use. So these SIMD processors actually are one of the 4 main categories of computers that Mike Flynn introduced or discussed in his paper in 1966. The first type is, the first category are the SIMD machines. This means single instruction, single data. This means that I have one single instruction and I go to memory and get one data element and operate on this data element. I do whatever this instruction says that I have to do. That's what a sequential machine does. Like what, if you go to your laptop or to your cell phone and you look at the CPU that you have there, probably that CPU will be a multi-core CPU, but if you focus on just one single core of this will be a sequential machine, a SIMD machine that can only execute one instruction on one input data element, maybe one or two, right? Because if we are adding 2 elements, we need 2 input operands and we will get 1 output. The second group are the SIMD, single instruction, multiple data elements. And these are the ones that we are going to talk about. And as you will see very soon, there are 2 main types, array processors and vector processors. They are very similar. They have a lot of things in common. That's why we explain both together. What's the main idea here? The main idea is that if I want to add these 2 vectors, A and B, and store the result in C, I just need one single instruction, add, and store, right? Just need one single instruction for the million elements. So that's why it's single instruction, multiple data. The third category is MISD, is multiple instruction, single data. It's not easy to find computers or machines which follow this paradigm these days. Probably the closest thing is the systolic array, are the systolic arrays that Professor Mutlu explained in the last week. Another example that you can also find, maybe search yourself, are Micron's automata processors. They are also kind of similar thing. And the last category are the MIMD, multiple instruction on multiple data. And for example, I would say that the easiest example that we can talk about here are multiprocessors, multi-core processors, or multi-threaded processors, whatever you want to call them. And this is when we have different threads of execution and each thread can be doing a completely different thing. Tomorrow, when we talk about GPUs, we will also relate the way that GPUs process instructions with MIMD, because even though they are mostly SIMD, they also have some features that are related to MIMD. Okay, anyway, let's start talking about SIMD. Yeah, go ahead.
Would a single data element refer to a data element as an array, for example, or as an integer? Yeah.
Could you repeat?
Here it says on a single data element. Do you mean the smallest possible element, like an integer?
Yeah, it's a scalar value, essentially. Mm-hmm.
So an array.
If it's an array, if we operate on an array, then it's a SIMD machine. Okay? Okay. Data parallelism. Let's define what we understand by data parallelism. I think that I somehow already defined that. But data parallelism, in data parallelism, the concurrency, that is the ability of execute several things, several instructions at the same time, or several operations at the same time, arises from performing the same operation on different pieces of data. That's SIMD, and the best example is the vector addition that I mentioned before. Another example can be a dot product of two vectors, right? In dot product, I can also have some sort of independent computation on the different elements, at least for the multiplication part. For the accumulation, yeah, we could discuss about that. We are not going to talk about that right now, but it's another possible example of SIMD computation. You have to contrast this regular data parallelism with something that has already been covered in the course as well. It's data flow. In data flow, concurrency arises from executing different operations in parallel. And the computation can be completely irregular, right? This is computation in a data-driven manner. And also contrast with thread or control parallelism. It's the example that I gave you before about the multi-core processors. In multi-core processors, we can have individual threads running on each of the cores, and they can be doing completely different things. Maybe these different threads might belong to the same program, to the same process, or maybe even completely different processes, completely different applications. So here in SIMD, we exploit operation-level parallelism. We could say that it's a form of ILP, instruction-level parallelism, but not in the way that ILP is exploited, for example, in a very long instruction words architectures, right? Here, it's a much more simple this data-level parallelism, because the multiple instructions are essentially the same instruction on different data elements. Okay, a little bit more. Single instruction operates on multiple data elements in time or in space. We are going to have multiple processing elements. You're going to see that in the next slide. And we say that we have a time-space duality. Depending on if we operate on, let's say, time, or let's say we exploit this regular data parallelism in time or in space, we will be talking about array processors or vector processors. You have the definition here, but the best way to understand it is going directly to this slide. You can already observe the difference between these two array processors here on the left. They have, let's assume for now, 4 functional units or 4 processing elements. I will probably use these terms as synonyms, right? Processing element, computing element, functional unit. I hope it's always clear. So you have here 4 processing elements that are exactly the same. Each of them has a different number, index, of course. And here in the vector processor, you also have 4 processing elements, 4 functional units, but each of them is specialized. Let's take a look at how they execute the code, but first of all, let's take a look at the code. So here we have an instruction string, 4 instructions. The first instruction is a load instruction, and we call it a vector load. Why is that? Because in the same access, when we execute the same one single instruction, we are loading from memory more than one element. In this case, 4. Okay, as you can see there, we are going to wherever array A is in memory, and we are getting 4 elements at the same time, A0, A1, A2, and A3, and we are storing them in a vector register. This vector register, you can think about it like a very, very long register, which is, in this case, divided into 4 slots, and in each of these slots, we are going to place A0, A1, A2, or A3. The length of each of these slots will be typically 32 bits or 64 bits, right? As usual in, the scalar registers that we have studied in the LC3 or in MIPS. The second instruction is the vector add. In this vector add, what we are doing is to each of these 4 elements that we have in the vector array, we are adding 1. Next instruction is vector multiply. So we multiply by 2 each of these 4 elements. And finally, after having done all the computation, we store the 4 elements at the same time in memory. So how is this code executed in the array processor, in the vector processor? So in the array processor, each of the processing elements can execute any type of instruction. First instruction is load, so the 4 processing elements are loading from memory. One cycle later, let's say 1 cycle for now, probably this will take longer, right? Accessing memory, unfortunately, takes more than 1 cycle. But let's consider that this 1 cycle for now. We execute the add instruction, and we do the add operation on the 4 elements that we previously loaded. After that, multiplication, and after that, store operation. In the vector processor, because we have specialized functional units, we need to execute all the load operations in the same unit. So in the very first cycle, we issue load 0, is reading element A0, after that A1, and after that A2. But observe that as soon as we have read element A0, we can start executing this addition, right? That's why we see this add 0 here in functional unit add. So, and in the second cycle, while we are issuing load 2 in functional unit LD and the addition 1 in the functional unit addition, we can start with the multiplication in this third functional unit. So that's more or less how it works. And we will complete, after some cycles, we will complete the execution of the entire code for the 4 input elements. Observe that here in the array processor on the left, we have the same operation at the same time. So in any given cycle, in all the processing elements, we are executing the same operation, while in the vector processor, in the same cycle, we are executing different operations. That's with regards to time. Recall the time-space duality. With regards to space, in the array processor, we have different operations in the same space, while we have the same operation in the same space for the vector processor. So these are essentially the most significant differences between array processors and vector processors. The interesting thing here is that, let's say that this is like a kind of purist distinction. So real-world SIMD processors are a combination of both, and actually that's the case in GPUs, as we will continue discussing today and tomorrow. Let's very briefly compare and recall what's very long instruction word architecture, also to understand what's the main difference between SIMD, in this case the example will be with array processor, and very long instruction word architecture. Recall that in VLIW, what we have is a very smart compiler that is able to extract parallelism, typically regular parallelism, from the code and generate some packed instructions that contain several instructions, right? In this case, for example, in the same instruction, we have add, load, move, and multiply, and these 4 instructions will be executed in parallel in these 4 processing elements that you can see in the slide. So the concurrency here is coming from the execution of different instructions on different processing elements, while in the array processors, because they are SIMD processors, we have 1 single instruction. In this case, it's a vector addition, and what we do is executing the addition for different elements in each of the 4 processing elements. Is that clear? Okay. Let's continue. Let's go a little bit deeper. Our first example, and this is actually, it's still sequential code, right? So, but it's a very good example of what is called a vectorizable loop. Why do we call this a vectorizable loop? Because We call it a vectorizable loop because all the iterations of the loop are independent. There are no loop carry dependencies. So I can operate in parallel on A0 and B0 and on A1 and V1, right? That's why it's vectorizable, because I can easily convert this into something, some code that will be executed on a SIMD processor. So in the vector processor, we operate on vectors, not on scalar data, related to what he asked before. And there are some basic requirements. There is a need to be able to store and to load and store vectors, and we do that in the vector registers. Actually, we are going to use this nice thing today, and we are going to see the first example right now. So we have vector registers. I already mentioned or defined what the vector registers are. We are going to contain different elements coming probably from the same array in these vector registers. And these vector registers are going to have one certain vector length. And what's the vector length? Recall the example that I gave you in the beginning. Let's consider vectors of 1 million elements. Unfortunately, we cannot have machines with 1 million processing elements, but we can have shorter machines, and we will shorter machines with a certain number, let's say 128, 256 processing elements, and what we will do is using them at the same time. This is what we are going to call the vector length, okay? And the next thing is that we will need to access memory, and we are going to access this memory with a certain stride. In principle, you can assume that this stride is 1, like as in the example that we saw before, where we access A0, A1, A2, and A3. The stride between these elements that are accessed is 1, right? But we could be accessing A0, A2, A4, for example, and in this case, our stride will be 2. You had a question.
All right. The vector length is the software vector length. So if I have a software or I'm writing something with a vector of size 1000, would that be split on multiple vector registers? Or?
That's a very good question. Actually, the way that we are going to do this will depend on the machine. For example, we will see actually at the very end of this presentation, and we are also going to cover this tomorrow, but let me very briefly explain you. Some GPUs, for example, the NVIDIA Tesla GPUs that you're going to read about in this required paper for this week, they actually have, let's say, kind of software vector length, which is 32, but the truth is that you only have 8 functional units. So if your array is 1 million elements, you will go 32 by 32, but the hardware will be actually executing 8 by 8. But you will see an example later. Okay, let me very briefly explain a little bit better what this vector length and vector, well, at least vector stride is with this example. Does it work? Yes, okay. So this is our memory. This is address 0, this is address m-1, and we will use a certain vector length, okay, let's say 50, for example, and we have to set certain vector stride. This vector stride is going to be a register where we put one number, and this number means the distance between elements that are going to be accessed from memory. In the easiest example, as I said before, you can consider that this vector stride is 1. So if this vector stride is 1, and let's say our array A starts here, we are going to access this element 0, element 1, element 2, and so on, right? If we execute one vector load A, what we will be doing, this is our vector register, and this vector register is divided into several slots. For now, let's assume that the number of slots is VLAN, okay? So if our stride is 1, we will access address A, which is this one, A plus 0, and we will store it here, and then a plus 1, so we will read this and store it here, and then a plus 2, and so on, right? If we set the stride to, let's say, 8, we will access a0, but then a8, and then a16. So the addresses that our load functional unit is going to generate are address a plus 0, a plus 8, a plus 16, and so on. So we will be reading this thing and put this here, this thing, put this here, this thing, put this here, and so on. Okay? So this thing is the stride which defines what's the distance between consecutively accessed elements. Okay? We will continue talking about the stride later. Okay, there we are. Okay, so let's continue. A vector instruction performs an operation on each element in consecutive cycles. That's what we have seen in the example before, but there is something good here. Recall, the operation that we execute on every element stored in a vector register is independent from the other operations on the same vector register. So that's why we can allow deeper pipelines. Recall that we have studied here the MIPS pipeline, for example, right? It has 5 stages. We can have even deeper pipelines, and that's going to be very good to increasing the throughput of the machine. And why can we have these deeper pipelines? Because there is no intra-vector dependence. So if I operate on A0 and on A1, I can do it at the same time because they are not dependent instructions. They are not dependent operations. So I won't have to worry about things like hardware interlocking. Recall in the pipeline and this lecture about pipeline issues, if you have 2 instructions that are depending on each other and they are executing in the pipeline, at some point you will have to stop the pipeline, right, to what is called a stall. And so we don't have to worry about this here. We don't have to worry about control flow because even though, so this is pipeline operating on different elements and it's one single instruction. There are no branches there, so we don't have to worry about them. We will use branches as well in SIMD programs, but the number of branches will be much smaller. They will be much more infrequent. And also the thing I already mentioned that calculating the address is very easy. Why is that? Because we are defining a stride, and using this stride, we calculate A plus 1, A plus 2, or A plus 8, A plus 16, and so on, right? The good thing is that because we know exactly what are the addresses that we are going to access, we could be doing something like prefetching. And what does prefetching mean? Have you ever heard about prefetching? This essentially means that if I know, probably you have, some of you might already have used that when programming in C. The thing is that if you know exactly what you are going to access in memory, from memory in a certain number of cycles, you could start the access already, right? So here, and going back to the example that we were discussing, I have 1 million elements I want to operate on, and I know that right now I can operate on 32, but after that I will be operating on the next 32. So while I'm doing the computation for these 32 elements, I can already be accessing the next 32 elements from memory. That's what is called prefetching, and there is a lot of research on this, and this is something that nowadays, all computers or all CPUs include hardware prefetchers. But this is, let's say, like more advanced concept in computer architecture. So if you are interested, you can come to the computer architecture master's course and the bachelor course that the bachelor seminar that Professor Mudlu teaches as well.
Is that a compiler level optimization, or can that be done in hardware? Detection that I can prefetch something?
Yes. So either way, you can have software prefetching. Your compiler can detect that and can generate these instructions, these load instructions to go to memory and bring the data, or even easier if the hardware does this for you and for the compiler. That's actually the way it is in current CPUs. Okay, advantages of vector processors. I think that this is something that we are already talking about. There are no dependencies within a vector, so pipelining and parallelization work really well. Deep pipelines, we were already mentioning that. Each instruction generates a lot of work. One single instruction can be useful to operate on, let's say, 32 elements, or let's say 128 elements, depending on what's your vector length, right? And this is definitely useful, because remember that in this, how was it called? How was it called in the lecture? The cycle, the instruction execution cycle, right? Recall that the very first thing was instruction fetch, go into memory and bringing the instruction from memory. So this is something that here it's going to be much more efficient, right? We need to read, so the number of instructions that we need to read from memory is much smaller. If we have a scalar machine and we have to operate on 50 elements, we need to go 50 times to memory to read the instructions to operate on these 50 elements. But if we have a vector machine, we only need to go once, right? So that's why here we say that we reduce the instruction fetch bandwidth. Also, regular memory access patterns. This is what it will be typically. We will define a stride, but after that, the accesses are always regular. And even though we don't really need to cover the reasons why, but it's much more efficient memory access. And then there's no need to explicitly code loops. We will use loops, and actually we are going to see an example at the end of the lecture, but we will have fewer branches. In the end, think that branches are not productive, right? They are, of course, necessary because we need them to control the flow of the program, but they are not really necessary. I mean, necessary they are, but they are not really productive, right? Productive is executing additions or executing multiplications. That is really productive. But they also have some disadvantages. Disadvantages is that they are not good for exploiting irregular parallelism. And actually, GPUs, for example, are not really very good at irregular parallelism. You can, if you're a smart programmer, you can figure out a way of extracting the parallelism and still getting good speed up as compared to a CPU, but it takes obviously more effort. And that's actually something that was already pointed out by Fisher when he was working in these very long instruction war architectures, and this paper published in ISCA 1983, where he said, to program a vector machine, the compiler or hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware, right? We need regular data parallelism. And we need to be able to write the code in a way that we access this regular data organization in an efficient way, and we put it in the vector registers in an efficient way. And continue saying it's not only hard to do in first place, but just as hard to change. That is, you might have written your code for, let's say, vector length equal 50, and eventually you need to change this because for some reason the characteristics of your array change, right? So you will have to go and change the code. So this is one of the main disadvantages of these vector processors. And they have more limitations. They can easily become, so a memory can easily become a bottleneck. Why is that? Because I have a lot of compute power already, right? In the examples that we are discussing here, we have, for example, 4 processing elements, and these 4 processing elements can be computing at the same time. So if I need to feed these 4 processing elements, I need to read 4 elements at the same time from memory, right? So I need higher bandwidth. And actually, if you go to any of the, GPUs, for example, most of the workloads that we execute nowadays on GPUs, they are bounded by the access to memory, even though if you read the specifications, you will see that the bandwidth is amazing, like, I don't know, 700, 800 gigabytes per second. It still is short for what the computing elements of the GPU need. Okay, a little bit more in depth. Now, let's talk about the vector registers. Each vector data register holds n bit values. Let's say typical values, if our vector length is 32, n will be 32. If we operate on 32-bit elements, 4-byte elements, like integer or floating point, they will be, this m bit will be 32-bit, right? And here you can see 3 vector registers, vector register 0, 1, and this will be whatever, x. So, and we also have 3 special registers, which are the control registers. Vector length, we need to define what's the length of the vector that we are going to operate on, the stride, which we have already defined, and the vector mask. So so first of all, vector length can be a maximum of n. This is something that we have already discussed. In an example that we will see later, this vector length will be 50, but then at some point we will see another example where we will have to reduce this vector length to be effectively 15 in the example that we will show. And then we have this vector mask. Why do we need this vector mask? Because sometimes, unfortunately, we cannot exploit all the lanes or the functional units at the same time. And why is that? Because life is not so regular, right? So we need to somehow be able to decide when do we really want to operate on some specific data element or not. And that's why we need to use a mask. And actually, I'm going to introduce here a very important concept that unfortunately Professor Mudlu, I think, couldn't cover when he explained branch prediction, and this lecture that we recently have, and it's called predication. And we are going to see why predication is important, because it's used in vector processors. Let's consider some C code, some high-level language, something like this. I have an if, and I have, let's say that we are going to operate on a vector processor 0, but for now this is just scalar code, right? Just sequential code. And if V0I is 0, I will do this. If not, else I would do that. You already know that the compiler for a sequential machine, for a SIMD machine, will convert this into something like, for example, let's invent some useful ISA. For example, branch equal 0. Branch equals 0 this will be a conditional branch, so we will jump if V0I is equal to 0, right? If it's not, we won't branch, and we will do this. But if it's not 0, we will go somewhere where the else label is, and we will do that. Of course, we also need some unconditional jump here, right? And after executing the do this, go to the end of the program. So how is this going to be executed on a SIMD machine? We don't need to have branches like this one and this one. We are going to use predication. And predication consists in having a special register called vmask, which contains 1 bit per functional unit. And the value of this bit obviously can be 0 or 1. And it will be 0 or 1 depending on the predicate. What's the predicate? The condition here, the condition here. So vmask will be equal to 0 or 1, depending on what's the value of V0I. So for example, if V00 is equal to 0, this will be 1. If it's, the next one is equal to whatever, it's not 0, this will be 0, and this will be 1, and this will be 0, and maybe this one will be 1. Okay? And then we will execute do this. But the hardware will only execute this do this for those lanes or those functional units where vector mask is equal to 1. And after that, we will obtain the complement of vmask. So vmask will be 0, 1, 0, 1, and so on. And then we will do that. So this is how predication works. Oh, is that better? Very good. Okay, so this is how predication works. We will see another example at the end of the lecture, and probably, yeah, on tomorrow as well, when we talk about the GPUs. Okay. We said we will have deep pipelines, okay, something like this. So all these functional units, they will be pipelined. Why is that? Because they are in V1 and V2, I have the input operands. In V3, I want to store the result. Each of these V1, V2, V3 are divided into slots where I'm going to have these individual m-bit operands. And in each cycle, I start executing one multiplication in this example, so that in each of these pipeline stages, 6 in this case, I have the specific computation, whatever the stage is for each of the operands that I have in the input registers. Okay? First example of real-world vector machine is CRAY-1, which was released in the 70s, probably the first supercomputer, and it was the fastest computer of its time. Observe that this is in this schematic that we have here. We can see here the vector registers. We have also here some vector functional units. Even this VM is probably the vector mask. But also this machine, it was the fastest, not only because it was a vector machine, but also because it was the fastest scalar. It has the fastest scalar processor of its time. So you can, that's why you can also see here some scalar registers and some scalar functional units. And why is that? Because recall Amdahl's law. Maybe your code is great, is highly parallelizable, vectorizable. You can extract a lot of parallelism, regular parallelism from there. But if some part of your program is inherently sequential and there's no way of parallelizing it, your maximum speedup will be limited by Amdahl's law. You already know that. Seymour Cray also knew that, and that's why he put a lot of effort on designing a very powerful scalar core as well. If you want to see a Cray with your own eyes, you can go to CAP, to the building where our lab is, and you will find this beautiful Cray XMP28. I think this one was built in the 80s, and also you can see next to it this Raspberry Pi, which has exactly the same, around the same computing power. So this is how we evolved. And here you can see some, I mean, there next to the machine, you can also find the data sheet here. These are just some figures from it. In this particular case, observe that this one has 4 scalar CPUs, so it was already multi-processor or not exactly multi-core, but multi-processor. And here you can see vector registers, scalar registers, functional units, etc. A little bit more information here for different models, the number of CPUs, size of the memory, number of banks. We are going to discuss what the banks are right now. And more details about the functional units, and even more about, mainframe, input-output subsystem, and storage device. So, and this is Seymour Cray, the father of supercomputers, and the nice thing that he said is, if you were plowing a field, which would you rather use, 2 strong oxen or 1024 chickens? Well, it will depend on what your field is, right? It will depend on what your computation is about. If you have a lot of regular parallelism, you will probably go for this. If you don't have so much parallelism, but you need a lot of computing power, you will probably go for this. So I think that we are going to stop here for 10 minutes. And we will start talking about the memory access, memory banks. Okay. Yeah, let's continue. We already had 10 minutes. We were here, and now we are going to talk about how we access memory, and we will see why we need memory banks and why we need to have an interleaved memory in order to have an efficient access to memory. And that's why the reason why is because we have vector loads and vector stores. So we need to be able to access many elements at the same time for read or for write. For now, we are going to assume the simplest case, the stride is 1, and all the elements are going to be loaded into consecutive cycles, as you will see. And the way to achieve this is by having these banks. By having memory banks, we are going to be able to get from memory 1 element every cycle. And this is something that without banks is not possible. And why is that? Because unfortunately, accessing memory takes usually much longer than 1 single cycle. This is how banked memory or interleaved memory looks like. Instead of having 1 single memory thing, a monolithic array with 1 single MDR memory data register and MAR memory address register, we are going to have a number of banks. In this example, 16. And each of them, as you can see, has its own MDR and MAR. They still share some important components as the data bus and the address bus. So let's discuss how we are going to access them. The first thing to think about is how are the memory addresses going to be mapped into these banks, right? Because if you have some sort of monolithic memory, something like this, let's say that this is our memory, this is element 0, this is element n-1, and I know that this is address 0, this is address 1, this is address 2, and so on, and this is address n-1, right? I have my MAR, I have MDR, and if I want to read some specific address from memory, I will put this address in the MAR, and sometime later I will get the value from from the memory and store it in the MDR. Sometime later, how much is? It's a memory latency, and this memory latency, it's going to be M cycles. So what's the problem here? The problem is that if I need to access 10 elements, I will have to wait in total 10 times M cycles, right? So the way of reducing this latency is by having a banked memory. And in a banked memory, I divide the monolithic array into something like this, as you also have in the slide. These are the memory banks. This is bank 0, 1, 2, up to, let's say, bank 15. Maybe we, instead of having 16, we can have 8 or we can have 32 banks, okay? And now the way that we are going to map the addresses into these banks is by doing it in an interleaved way. It's one possibility. This doesn't mean that always going to be the case, but probably it will be the most usual case. So this way, address 0 is here in bank 0, address 1 is in bank 1, and here we will have address 15, and here the next address is address 16, address 17, and so on, right? And this is address 31. So each of these banks has its own MIR and MDR, MIR, MDR, MIR, MDR. They are sharing the address bus, they are sharing the data bus, and if I want to access, let's say, 16 elements, and let's assume for now that our stride is equal to 1, if I want to access 16 elements, what I will do is, in the very first cycle, I'm going to issue the memory load for address, let's say, 0. So I will put address 0 here, and I will start accessing this thing. How many cycles do I need to access this element in address 0? Well, maybe I still need m cycles, right? But the good thing is that one cycle later, while I'm accessing this element, I can start the access for address 1. And then I can start the access for address 2, and so on. And if, for example, this m is equal 10, in cycle 10, or let's say this is equal 11, in cycle 10, I will get the data element that was in address, or that is in address 0. And then I might issue one more data load, and here, one cycle later, I'm getting data element in address 1. You see? So this way, I can fetch one element every cycle. So after having paid, let's say, the latency of the first access, these 11 cycles here, I will have one data element every single cycle. You see? So my bandwidth, it will be much higher. There is another advantage here. You know that to access memory, I will probably need some address decoder, right? And with the address decoder, essentially, I mean, here I will have the address, and then I will activate the corresponding address, right? Observe that this address decoder needs to be very, very big. So if it's so big, I will, the latency will be higher, right? So if the latency is higher, this M cycle will be a very high number of cycles. But here, the address decoder is much smaller. So probably latency will be much smaller, and probably also these M cycles will be lower than these M cycles here. So that's another advantage. Okay, let's go back to the slide. And here you see one more picture, the memory, 16 memory banks, and here you can see on the right the the unit that we need to compute the address. In vector machines, this is also very easy, very lightweight, because we usually have one base address and we start adding one stride. It was stride 1 in our previous example, but it can be something different depending on the value that we put in this special vector stride. What was it? Stride vector, or yes. I mean, let's recap a little bit. What do we need to get one element every cycle? First of all, in this example, we are considering a stride equal to 1, because if we have a stride equal to 1, we will be accessing address 0 here, address 1, address 2, and so on. So we can access all the banks in parallel. We need also that the consecutive elements are interleaved across banks, exactly as I was already assuming. And another important thing is that we need that the number of banks is greater or equal to the bank latency. Observe that in the example that I just gave you here on paper, we are assuming a latency of 11 cycles, right? And with these 11 cycles and 16 banks, we can get one element every cycle as soon as we start obtaining elements from the memory. Now think that instead of having 16 banks, we only have 8 banks. What will happen? We wouldn't have enough number of banks to compensate for the entire latency of the first access. So we would have started 8 accesses to each of the 8 banks, and still we'll have to wait 3 more cycles to get the first element from bank 0. So in order to have an efficient memory access, we need to have a number of banks that is at least as high as the memory latency for each of the banks. That's one important consideration. Another important consideration is the stride. Observe that here we were assuming a stride 1 and we were assuming a interleaved layout, right? So with this layout, now let's consider that instead of accessing address 0, 1, 2, and so on, we need to access the stride is equals 16, and then we need to access address 0, 16, 32, and so on. What would be the problem? The problem is that all these addresses are here in bank 0, you see? So this is what we call a bank conflict. And the problem is that we cannot have accesses in parallel to different elements. We will need to first access 0, wait for the 11 cycles, and when we have element 0, we go to address 16, wait for 11 cycles, and so on. So this is one of the drawbacks of having banked memories, but I mean, still there are ways of dealing with this, and we will talk about them later. Now, let's continue with the slides, and actually we are going to see some code, start studying some code. This is some scalar code. Observe that in whatever ISA this is, we have one vectorizable loop, and in this vectorizable loop, we are going over 2 vectors of 50 elements, and we are calculating the element-wise average of these elements and storing the result in vector C. If we translate this or compile this into some ISA or scalar code, will be something like this. Here you can see, first of all, move to register 050, which is the number of iterations, number of times that we are going to execute this code. Here in register 1, the address A of array or vector A, R2 equal B, R3 equal C. We need, let's say, just one single cycle for all these, for these 4 instructions, for each of them. And then we start this loop, right? And in the loop, the first thing to do, we assume that this is memory access, memory load plus auto increment. And we need 11 cycles for that. To go to memory, address array A and read something into register 4, go to memory to address that is stored in register 2, which is the address of register B, vector B, store it in register 5, then we add these 2, then we shift to the right, then we store the result, and here we evaluate this, the value of R0, which we are decrementing every single iteration, and if it's necessary, we will jump and continue the execution for 50 times, right? So this is the latency of all these operations, all these instructions on a system machine. If you count the number of dynamic instructions, the total number of instructions that will be executed here, it will be 304. And you can already also compute what's the total number of cycles that we will need to execute this in a machine. If you do that, you will obtain that number, 2004 cycles. And this will be assuming that we have a monolithic array as the memory, one single bank. Because we want to be fair, and in the vector example, we are going to use a banked memory. We can also do the same, and have a banked memory or interleaved memory for the scalar processor. Let's assume we have 16 banks, but here, if you go back, you could have, for example, 2 accesses at the same time. If we assume that array A is in bank 0 and array 1 is in bank 1, we are only be able to do 2 accesses in parallel, because that's what we have here. And if you assume that, you can calculate what's the total number of cycles, and you will see that the value that you obtain overlapping the 2 load accesses, as you can do if you have at least 2 banks, you will obtain 1,504 cycles. We assume 16 banks. I don't need to explain this because I already explained it on paper. But if you have any questions, you can, of course, ask. And now let's take a look at what happens when we generate vectorizable code or vector code for a SIMD machine. Our code will look something like that, right? Observe that first thing to do is setting the vector length equal to 50, let's assume that we can have vector length equal to 50, okay? We can later discuss, what if you only have 32 functional units? Yes, of course, this is something that we can discuss, and we will do it at the end of the lecture. But for now, let's assume that we have 50. Let's assume that, well, it's not assume, it's what we need for this code, actually, because in this for loop, 50 iterations, we are accessing always consecutive elements, so our vector stride is 1. Then we have here, these two instructions are two vector loads. We go to array A or vector A, we read something and we put it in vector register 0. Then we go to B, read something, put it in vector register 1. And then we have the vector addition, vector shift right, and vector store. Here, you have the latency of all these instructions. The first two instructions are scalar. They only take one single cycle. There's no vector execution here. Why is that? Because we are just updating one single register in the whole machine, right? Which is VLEN or vstride. But the other instructions are vector instructions, and the way that these vector instructions, recall that slide where we have the different functional units, and we somehow pipeline the execution of the different, for the different vector elements. What we need to do is the same as we were doing for memory. We will have to pay the latency of the very first access to memory, or the very first computation for the first element in the vector array, and after that, we will be obtaining one new element or one new result every cycle. That's why we have this, in the case of the vector load, 11 plus VLEN minus 1. In the case of, for example, vector add, 4 plus VLEN minus 1, assuming that the latency of one add operation is 4 cycles. And this is in total only 7 dynamic instructions. So compared to the 304 that we had for the scalar code, only 7. So we only need to go to memory 7 times to read an instruction. And you will see that this is also much faster. For now, we assume that there is no chaining. What does this mean? This means that we cannot do data forwarding among or between different consecutive instructions. We will see in more detail later. So essentially, this means that if I execute this vector load, first vector load, no, okay, I execute the first vector load and then the second vector load. Observe that I need to execute both before doing the addition, right? The way that I execute these two instructions is by accessing memory. I need 11 cycles for the very first element, plus 1 cycle more for each of the remaining VLEN minus 1 elements. This means that right after 11 cycles, or right after 22 cycles, let's say, I can have the first element of V0 and the first element of V1. So this means that I could already start doing the addition for this first element of V0 and V1. If I do that, I'm assuming that I have vector chaining. That's kind of data forwarding. So for now, what we assume is that we have to wait until the very first vector load has completely finished. The second vector load has completely finished for the 50 elements that the vector length tells me, and only after that I can start executing the addition. And that's why this will be the timeline. This is the way that we execute this. That will take 285. Let's take a look here, because it's going to be easier if we look at the code here. So can you see it? More or less. Okay, I think this is better. Okay, so look at the timeline. First of all, 1 cycle. This cycle is for what? For this move instruction, a scalar instruction, 1 cycle. Second cycle for the next scalar instruction. And then I have first vector load. For the vector load, recall how we had to access memory. we put the address in the memory port on the MAR of bank 0, and we start accessing memory. We need 11 cycles for the very first element, and then we will start obtaining one element from the remaining banks every cycle, right? And that's VLEN -1, which is 49. So this is what I need to execute this first vector load. Because I only have one single memory port, this means I only have one single MIR and one single MDR in each memory bank, I cannot start executing the second load until I finish with the first one. So that's why after that I will have 11 plus 49. And because we are assuming that there is no vector chaining, even though, observe that here, we already have the first element from V0 and the first element from V1, we cannot start with the addition until we have finished completely with the two loads. And then we start 4 cycles for the first element of this vector add, 49 more for the remaining elements, VLEN -1, and so on. So if you calculate, you add all these numbers, you will obtain these 285 cycles. Is that clear? Any question? I think you will need to think about this yourself a little bit, and yeah, I think that when you think about the example, you will see it very clearly, and it's very important to understand this very well. Okay, now let's assume that we have vector chaining. That is, as soon as I get the element 0 of V1 in this example code that we have here, as soon as I get it from memory, I can forward it to the next functional unit, which in this case is multiply. I don't even need to write to the vector register. I can directly forward it to the multiply unit. And when I'm done with the result here that I'm going to store in some of the slots in V3, I can chain and store in the, and start the computation of the next addition. So if I do that, observe that the good thing is, as I said before, as soon as I finish with this 11 cycle, which correspond to the load of the first element of the second vector load, I can start the addition. That will take 4 cycles plus 49, which is vector length -1. And as soon as I'm done with this addition, I can start the next instruction, which is the shift right. You see? So this way I can reduce the number of cycles a lot. But still observe that I cannot have accesses to memory in parallel. Actually, even here, this is a store operation, even though the result for the first element of the vector register is completely done here after executing the shift right, I have to wait a few cycles until I start the store operation. And why is that? Because I have one single memory port in each bank. I only have one MIR and one MDR.
The memory latency of 11 is because after you read, you only have to wait 10 cycles until you get it translated, right? Did I get that right?
The 49, you mean?
No, the 11.
The 11.
The first address into the MIR, it takes 10 seconds or 10 cycles to get it out.
Yes, I had.
But shouldn't you then be able to start putting the second addresses into the MIR of the second vector right after cycle 15?
You need to have the value in the address in the MIR after you until you complete the entire memory access.
You can't just write a new one in.
No, you cannot, let's say, save those nanoseconds or whatever. For that, what you need is what we are asking ourselves here. And the way to do that is using, let me show you the example, using multiple ports. I have bank 0 here, bank 1, and so on, 15. Recall that for each of these, I have one MIR and one MDR. I have also for bank 1, I have also for bank 15. And now what I could do is adding a second memory port, for example, with second MIR and second NDR. So I can be accessing memory, 2 addresses from each bank at the same time. And this is the way that I can have, I can improve the memory access a lot. And that's what we have down here. And that's why still recall that we have one single address bus and one single data bus. So that's why we can start this second vector load only after one cycle after the first vector load started. But using the second port here, the second load port, because actually in this example we are considering 2 ports for load and 1 port for stores, we can start the second vector load, and also because we have vector chaining, you see how efficient we can execute this code here, only 79 cycles, which is more than, or 19 times faster than the execution of the Scalar code. Okay? Okay. Yeah, let's continue. Questions. What if, question that you were asking before, what if the number of data elements is greater than the number of elements in a vector register? Because as of now, we have to say, okay, let's define vector length equal to 50, or let's say a vector length is equal to 32, right? But now we won't have 1 million elements, so we cannot operate on 1 million elements at the same time, right? So what are we going to do? We will need to break loops here. So if we have to operate on 1 million elements and the maximum vector length that we can have is 64, as is in this example, we will have to operate on 64, 64, 64. And now let's assume that the number of elements that we have to operate on is 129. If it's 129, we will first operate on 64 elements, we will load, add, store, and then we will jump. We still need jumps, we still need branches in the vector code to operate on the next 64 elements. And finally, the last thing to do, because the total size of the array or the vectors that we are considering is 129, we will have to change the vector length in my example to 1, in the example of the slide to 15, and then operate on this single element or these 15 elements, okay? This is what is called vector strip mining, and the reason is because it's somehow an analogy to what is called strip mining in mining, which essentially means that if you have a mine and you want to find gold, you will have to remove all the dust and all the dirt that is, I mean, rocks, etc., that are on top of the gold, right? In our code, the gold are the 64 elements that allow me to operate on all of them at the same time, taking advantage of all the functional units that I have in the system, while the dirt, what I really don't want to have, are these only 15, which are somehow wasting the power of the computing power of my machine. Okay, that was the first question. Second question, what if vector data is not stored in a strided fashion? That's also a very important question, right? Because for now we are considering, okay, let's have very efficient access. So let's assume that vector stride is 1, which means that we are going to access all the elements of the array. Or I also gave you an example. Let's now assume that vector stride is 8. Okay, but it still is regular, right? So I know that I have to access element 0 and then element 8 and then element 16 because my stride is 8. And recall that we could even prefetch because we could know that we will end up accessing element 32 and element 40 and so on, right? But this is not going to be the case in all codes, right? So that's why we need some way of using indirection, and this is what is called scatter and gather operations. I want to give you very quickly an example of what a scatter operations or gather operations are. And one good examples are sparse vectors. What is a sparse vector? It's a vector, let's assume that I have this in memory, vector called C, and it turns out that almost all the elements of this vector C are equal to 0, except some of them. For example, this one is 4, and then I have another one, it's 10, and then I have another one that is 50. And the rest of elements are zeros. So this is a sparse vector. So if I access it, let's say in a dense way, if I access it as if all the elements were useful, it would be a waste of time, right? And a waste of energy as well, because I would go over all the elements of the array, and maybe this array has 1 million elements and only 3 of them are useful, right? So what should I do here? Let's assume that this 4 is in address 1001, this guy is in address 2050, and this address is 3072. What I will do here is having a second array, let's call it D, it's an index array or vector, and this guy has 3 elements. And in these elements, what I have is the address of the elements that are different different than 0. So this element of D is pointing to this element of array C, this one to this one, and this one to this one. And if I want to do whatever with these 3 values here, the first thing to do is to access DI. And after having accessed DI, I will access array C. So if I want to get these 4, I have to add Z, which is the address of array C, plus D0, which is C plus 1001, equal 4. And for the next element, C plus D1, which is C plus 2050, which is equal 10, and so on, right? So these kind of indirect accesses are called scatter or gather accesses. In this case, in particular, it's a gather access because I have this in memory and I'm gathering it. I'm reading from memory, okay? When I'm writing, I talk about a scatter. And this is what you have in the next 2 slides. So, yep. This is an example of gather. Here, same as in my example, D is the index array, C is the array that has the values that I want to access. That's why the first thing to do is loading values from, loading the contents of array D, and with this array D, I do this load indirect to access array Z. You see? And now, example of the sparse vector that I already gave you, and this is the same but for scatter. Here the index vector, the vector D is that one. This is the data vector that I want to store. Let's call it B, for example. And this is the vector C where I want to store. What I do is I take this 3.14, I go to the index vector 0, and I store this 3.14 in the address base plus 0 being based equal to C. The 6.5 is in address base plus 2, I store 6.5, and so on. Okay? We need these instructions as well. As you can see, the memory access here is not so efficient, right? Because for every single read or write, useful read or write, I need to access memory twice. But still, I, of course, need it. And then conditional operations, we have already talked about that. Conditional operations is where we need to use the mask operations, where we need to use the vector mask. I already gave you this example as well. Here, this code is even simpler than the one that I used, because we simply have one if. If AI is not 0, then I will do this multiplication. If it's 0, I don't do anything. Yep.
So
putting the elements and scatters the...
Writing, yeah. Gather, scatter, okay? Okay, so mask operations, yeah, it's essentially the same example that I gave you before on paper. You see, for that particular code, vector load from A, vector load from B, I obtain the mask, and I will only execute this multiplication for those elements where we find the corresponding bit of the mask equal to 1. If the bit is 0, because they don't fulfill this predicate, then I don't execute the multiplication for them. And here you have another example that is more similar to the one that I gave you with if and else, and essentially the same thing that we have already seen. Compare and obtain the vector mask, compute whatever, do this, and then complement V mask, and then do that. Is that clear? Okay, yeah, and here you have the values of the vector masks. You can take a look. One more thing about mask vector instructions, because maybe you are asking yourself, okay, how do we really execute that on the hardware? We already know this bit of the mask. If it's 0, we don't do anything. If it's 1, we execute the multiplication or the addition. But how do we really implement that on the hardware? Well, there are two possibilities. The simplest one, which is less efficient but is simpler, essentially executes everything for every single element, no matter if the mask that you can see here on the left-hand side is 0 or 1. You just execute only if the mask is 0, you don't write in the output register. And if it's 1, you write. Okay, that's the simplest implementation. Good thing that the hardware is simpler. More efficient way, doing what is called the density time implementation. In this density time implementation, the first thing that we will do is going over the entire vector mask and only issue the corresponding operation, let's say the addition, let's say the multiplication, for those vector elements where the mask is equal to 1. That's why here in the pipeline you only see C1, so you only see exactly C1, 4, 5, and 7. Okay? Which one is better? Well, I hope that this one will be more efficient, right? Because you are saving cycles. You are not doing computation for nothing. The drawback is that here the latency for one single addition or one single multiplication will take a little bit longer, right? Because you need to first go over the entire mask and scan it, right? Inspect it before starting the computation. Okay, some more issues to keep in mind. This is also something that we have already discussed. Now we are going to discuss it a little bit more with an example, matrix multiplication. And we have strides, usually, yes. Oh.
In the previous slide, don't they, or shouldn't it take the same amount of time? Because if we have a parallel, if we're doing them all in parallel, doesn't matter if we're doing 10 in parallel or 5 in parallel, because the ones that are 0 don't do. What's the point of just doing 5 in parallel?
No, so what's the total number of cycles that you will need to execute this thing here? And what's the total number of cycles that you need there? You need, okay, whatever is your, let's say 4 is the latency, 4 plus VLM minus 1, right? Oh, yeah. But here is 4 plus only the number of lanes or elements for which you are really operating, okay? Okay, so let's go back to the discussion about the strides. Recall the example. If our stride is 1, perfect, because I will be accessing 1 element in each of the consecutive banks. But I already gave you the example. What if it's 16? We will have a 16-way bank conflict, which means that all 16 memory accesses will go to the same bank, right? So the latency will be 16 times longer. The total latency will be 16 times longer. And this is always something that is going to happen if, always if the stride and the number of banks are not relatively prime. So for example, if my number of banks is 16, 16 is a power of 2, right? So it's the only divisor of 16 is 2. If I'm using, let's say, an odd number for the stride, let's say 1, 3, 5, I will never have a bank conflict. So my access will be maximum efficiency. But if it's not, if they have some divisors in common, for example, 10 and 16, I will have some bank conflicts. And that's unfortunate, but that's the way it is. There are ways of dealing with this, as we will describe next. Well, just let me give you a very quick example. Let's consider the storage of a matrix, right? And we are going to, so the storage of, the way that we store a matrix, which is a two-dimensional organization in memory, can be in two different ways, at least. Row major and column major, what does it mean? Okay, think about memory. Memory, it's a linear array, right? No matter if we are using banks or a monolithic array, memory, it's actually something like this. Right? This is address 0, this is address n-1. And this will be address 0, address 1, address 2, and so on. And that's the way that the different locations or positions in memory are addressed linearly. But what if I want to store something like this, like a matrix, with a, I don't know, row size equal 5 and column size equal 4, right? Number of columns is 4, number of, so the other way around. Number of columns is 5, number of rows is 4. How do I store them? Should I do it row major, which means that element 0, 1, 2, and so on are going to be stored like this? Or maybe should I use a column major layout? If this is, because this is element 4, this will be element 5, this will be element 10, and so on. So another possibility would be to store here element 0, and here element 10, and here, element 5, and here element 10, and so on. Depending on the way that I store this, I can do row major or I can do column major. That will depend on the machine, that will might depend on the programming language as well. It depends. So for now, in our example, we are just going to assume that we use row major. And with this row major layout, we are going to multiply two matrices, matrix A and matrix B. So you know that if we want to multiply matrix A and matrix B, what we really want to do is, what we essentially need to do is calculating the dot product of row times column. So I will have to calculate the dot product of A0, which is the first row of matrix A, times the first column of B, this B0. Right? I do the dot product, I obtain a value, and I obtain the first element of matrix C, that is the output. But now what's the problem here? The problem is that I will use row major or column major for both, right? So both are going to be stored in memory in the same way. And if this is matrix A, and this is matrix B, and this is my memory, matrix A will start, for example, here, this is element 0, element 1, element 2, which is element 0, element 1, element 2. But for matrix B, that will start somewhere here, this is element 0, 1, 2, and so on, and maybe this one here is element 10, right? So I have element 0 of matrix B here and element 10 of matrix B here. So I have a stride. When I calculate the dot product of this thing and this thing, for A, that's good. I'm just accessing consecutive elements, so I'm accessing consecutive banks. But for B, I will have to access this element, and probably they will be in different banks, but at some point, unless this stride, which is 10, is relatively prime with the number of banks, I will have a bank conflict. I think that is something that must be already clear, right? So using strides, unless these strides are relatively prime with respect to the number of banks, I will have bank conflicts. Bank conflicts. So how can I deal with these bank conflicts? There are several possibilities. The straightforward one, let's put more banks. If we put more banks, what's the problem? My hardware will be more expensive, right? So probably it's not the best way to deal with it. Another possibility is trying to find a better layout. And this is not always possible, but in some cases it is. And this is important if you want to be, for example, a good GPU programmer, because there is one very useful type of memory in the GPUs, which is an on-chip scratchpad, which is actually a banked memory. And this is the typical thing that if you are a GPU programmer, you will have to optimize and take into account. Maybe some of you, if you have already tried to program GPUs, you might have already dealt with that. So what I could do for that, one way of optimizing the layout here and obtaining and having a better memory access for matrix B, what I could do is transpose matrix B, and then I will obtain BT, such that instead of having element 0 and then element 10 far away, I will have element 0 here, element 10 here, element 20 here, and so on. And this will be 1, 2, etc. The good thing of doing this is that in memory, I will have element 0 here, and this will be 10, and this will be 20, and so on. So now my stride is 1 also for matrix B when I multiply this thing and this thing. Okay? It's just one example of possible, let's say, software optimization to have more efficient access to memory. And then there are also some proposals, hardware solutions, like for example, something that was presented in this paper by Bob Rao, very, let's say, seminal work in 1991, which essentially is doing some kind of randomized mapping. So you don't really know what bank you are accessing, and you have some kind of hash function that for this address you go here, and for the next address you go there. And the good thing is that the total number of bank configs for typical applications is greatly reduced. Problem of having something like this in the hardware is that if you are the programmer and need to start trying to reason, okay, where is my address map? You don't know that, right? It's much more difficult to figure out, at least. Okay, yeah, let's continue. We are, I think, almost done with SIMD processors. Just recall that the distinction between array and vector processor is poorest distinction. Current SIMD processors like GPUs, they are more like a combination of both. Recall also this slide, probably we will also take a look at this slide tomorrow. And about how the instructions are really executed on the hardware. We have throughout the whole class, we have been talking about the vector length, and vector length means the vector elements that you can be operating at the same time, right? And one possibility is having something like this. I have one single functional unit with a probably deep pipeline, and I start issuing operations through this pipeline. First of all, I operate on A0 and B0 to obtain C0, and then for element number 1, for element number 2, and so on. The instruction is exactly the same. In this particular case, vector length is 8, but what I'm doing is obtaining one element every cycle. And actually, in the example that we discussed for this vector code is what we consider, right? GPUs these days are more like something like this. They are still pipeline, but you not only have one single unit, you may have more, let's say 4 in this example. So here, the good thing is that exploiting parallelism not only, or concurrency, not only in time, but also in space, right? And this is how this functional unit might really look. You see 4 functional units up in the top, 4 functional units on the bottom. They might be, for example, addition and multiplication, and observe that they have access to the same registers. This is called a partition register file. And essentially what this means is that in your machine, you have a lot of registers. And when you run your program, you will need a certain number of registers. And what the hardware is going to do is say, okay, what's my vector length? It's 50. Okay, let's divide the total number of registers by 50. And to each of these guys, I'm going to give the registers that they need. So that is why, in the end, what we are going to do is that in this all these lanes, which are the combination of all the vertical functional units that we have together, we are going to be executing for vector element 0, for vector element 4, for vector element 8, and so on. And the elements of lane 1 will be here, elements of lane 2 will be here, and so on. So it's somehow also interleaved, right? You can see it. And we will take a closer look tomorrow at this slide as well, but this is how we are going to execute on this type of machine, this type of mix between vector and array processor. Here, for example, we have our vector length is 32, but we only have 8 units, right? So we need, let's say, 4 cycles to issue each of these instructions for the 32 elements. We will continue tomorrow. Thank you very much for your attention.